Hi everybody. I'm back. Uh, so I tried to get my cat to come up here and have a chat with me, but he doesn't want to be on camera. So anyway, maybe he'll show up later. Anyway, so no cat for now. Let's get back to it. Next thing we want to talk about is motion of the atmosphere. All right, what causes winds? How do they blow? What direction? And that sort of thing. All right. So here's the core idea. Warm air rises, cold air sinks. We've got this convection pattern that we were talking about. And so the places where the atmosphere gets warmed the most, those ought to be the locations where you see the maximum amount of rising. Kind of makes sense, right? Places where the air is cooling ought to be sinking. So as a rough guess, you might predict that in the tropics, in the equator, where the sun is shining the most brightly, you'll have the most heating and the most rising. That turns out to be correct. And you might expect that near the poles, where it's colder, you will have sinking and downward motion. And that's kind of correct, but it turns out things are a little more complicated than that. But let's start off with a simple and easy to understand view of how the atmosphere works in terms of rising and sinking motions across the globe. And it's important for me to emphasize the first thing you need to notice about this figure is that this picture is wrong. All right? This is a first guess as to how the atmosphere might move, but it turns out to have some problems, which we'll spend a bunch of time discussing. All right? So the flow of the atmosphere is in three dimensions, so it's a little tricky to visualize. So what I've got here is a cutaway view with the globe here, and then a picture of kind of the layer of atmosphere over the top of it. It's important to realize that this atmospheric layer is vastly exaggerated in thickness. In reality, it's really only a couple of pixels on your screen thick, but we've made it look thicker so that you can actually see something here. Anyway, so the idea is that going up in the atmosphere is going in this direction, all right? Going northward is like this, southward is like this, and so on. All right, so if we say the tropics are hot and are being heated, and the air there ought to rise, all right? Well, so here we are sitting at the surface of the Earth, and warm air rises up into the atmosphere. Sure, but there's already air at the place where warm air is rising into. Well, that air has to go somewhere. It has to be pushed out of the way in order for new air to rise up from the ground. Likewise, if the air is rising from the surface and leaving the surface, new air has to come in from somewhere in order to replace it. All right? That means you can't just have up and down motion, you also have to have side to side motion that goes along with it. And the pattern that you ends up with is warm air rises, pushes air away to the north and south. All right? This north-south circulation continues up until you get to the cold poles, where the air cools and sinks down again. All right? Then it flows along the surface near ground level back to the tropics, where it rises again. All right? And you've got a overall pattern of rising, poleward motion, sinking, equatorward motion over and over. Notice I said poleward and equatorward rather than north and south, because the same thing is going on in the southern hemisphere. All right. So once again, I want to remind you that this picture is wrong. All right. If there were only atmospheric convection and the Earth weren't turning, then this is what the picture would look like. And in fact, this is very close to the circulation of Venus's atmosphere, Venus being a planet that is almost entirely not rotating. It's going very, very slowly. All right, the Earth is spinning, and the Earth spins fast. So what effect does fast spinning have on movement of moving objects? Well, I could, talk to you about this, but I think what I want to do is show you a couple of videos showing examples of this. All right. So what happens when you have motion on a spinning globe is you have what's called the Coriolis effect. All right. Things that are trying to move in a straight line will actually be moving in a straight line, but because you're looking at them from a platform that's rotating, you as you stand on the earth are turning in place, all right, as you go around the Earth, all right? Since your perspective is rotating, things that are moving in a straight line will appear to be moving in a curved path from your perspective. One great way to visualize this, let me see if I can start this video here. I may have to sub it in. Okay, here we go. All right, so what we've got here is an experiment from my lab in which I took a metal pie pan, all right, with some grid lines on it, and I have it set up on a rotating turntable, all right? The turntable spins around like a record player, all right? And the camera that you're watching this from is turning along with it. So the camera and the table are turning together, and so if you watch, you'll see the floor go by. The floor appears to be spinning, the pie pan appears to be stationary, but really the pie pan and the camera are both rotating together. Exactly like your perspective as you look at the ground as you stand on a spinning Earth. And I've also got a little marble here. And what I'm going to do is I'm just going to roll the marble across the tabletop, across the pie pan, and watch what happens. Right, so you see give it a push, and it doesn't go straight. It starts making curves. It spins and turns to its right, making clockwise circles. Let me give it another push. See that? It's weird. It seems completely wrong, but that's because your perspective as you are watching this is from a spinning, rotating position. When I'm watching this experiment and I'm actually in the lab, and I'm not standing on top of the rotating platform, all right, the marble just appears to go in a straight line to me. It's only because the camera is turning that things look weird, all right? Another good example of this is another YouTube video that's worth taking a look at. I'll try to put links in the description or something like that. You may have played on these playground merry-go-rounds. All right, so what we did was these people got a bunch of physicists together and just threw a ball back and forth between people that were sitting on a merry-go-round. Now watch what happens. All right.
While to someone sitting on it, the ball appears. To an observer above the merry-go-round, the path of the ball appears straight, while to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis Force, whereby to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
All right, so that looks pretty crazy, but remember that this is your actual perspective as you stand on the Earth. It's not so noticeable for you because you're not rotating very quickly, but you're rotating fast enough that it will strongly affect what you see in terms of the wind patterns in the atmosphere. And so, a pattern that's much more closer, the actual way that atmosphere moves is somewhat more complicated. All right. So, as before, warm air rises. All right. And then it begins to move north. All right. As it begins to move north, this Coriolis force kicks in and diverts it from its northward path and pushes it off to the right. As it does so, the air begins to accelerate and go from west to east in this picture. All right. So then the air sinks down and comes down to the ground again at a latitude similar to where we are now. All right. So we have fast westward moving air going from west to east. Sorry, not westward, eastward. Fast moving air going from west to east, coming down to the area where we are now. And that leads to, you know, a strong motion in the winds near our latitudes. The air tends to blow, the wind blows from west to east. All right. From there, the air has now sunk to the ground and returns back south or towards the equator. And as it does so, it gets deflected off to its right again, which in this case means that it gets deflected from its north-south motion off towards the towards the southwest. All right. And so we call these the northeast trade winds because confusingly, winds are named after the direction they come from rather than the direction they go to. But the trade winds in the northern hemisphere, all right, are the tropical winds, and they always blow very consistently from northeast to southwest. All right. Meanwhile, above in the upper layers of the atmosphere, we have motion from west to east. I'll show you a better description of that later on. All right. So the Coriolis force deflects the direction of the winds, resulting in northeast to southwest winds in the northern hemisphere tropics, southeast to northwest winds in the southern hemisphere tropics. And as we get up to higher levels, we encounter a situation in which the air can't actually go from the equator all the way to the pole. All right. The reason for this, and I'm afraid I don't have a good slide for this, is imagine if you've watched the Olympics, you have a Winter Olympics. You have an ice skater, and she starts doing a spin with her arms stretched far out. Okay, she may be spinning pretty slow. As she pulls her arms in, right, her spin speed increases and she starts going faster and faster. This is the idea of conservation of angular momentum. So as air tries to move from the equator, which is very far from the axis of rotation of the Earth, towards the pole, which is right on the axis of rotation of the Earth, it's just like the ice skater pulling her arms in. She begins to spin faster and faster and faster. And in fact, if the air went from here to here directly, it would end up going like faster than the speed of sound. And instead, you end up getting turbulence and instabilities and sort of complicated swirling storms that break up this pattern and prevent the air from going all the way to the pole in one go. All right. Instead, the air transfers its heat from one of these cells, the Ferrel cell to the Hadley cell, and then this next cell continues the trajectory, taking the air another part of the way, and so on. And so the atmosphere ends up with this sort of banded structure. All right. But the most important part to remember is the Hadley cell, all right, which happens in the tropics, in which you've got, let me show you another slide of this. All right. Near the ground level, due to the Coriolis forces, the air blows from the northeast to the southwest, or southeast to northwest, depending on which hemisphere you're in. When it rises up, that's the blue parts of these lines, it gets deflected off to the east, and we have in this area air blowing from southwest to northeast, with a strong, strong motion from west to east at these high up in the atmosphere. All right, so this leads to this sort of global wind patterns, and what I've shown you here is an idealized picture, all right? And it's worth taking a look at how this actually plays out in the real atmosphere. All right, so once again, the two core ideas about global wind patterns are down near the ground in the tropics, you have the trade winds that blow towards the equator and generally diagonally from east to west. Up in the upper parts of the atmosphere, especially as you go farther north, you have the westerlies. This is often called the jet stream. All right, and usually when you're on a plane flight, you have to worry about whether the jet stream is going in your direction or not. My flight tomorrow is going almost directly over the North Pole, so it's not going to end up mattering very much. But the jet stream generally always blows from west to east. All right, and that's an upper level wind pattern. So I have a cool website that allows you to visualize and see wind patterns as they move around. And I'd like to show you that so we can see what these trade winds and jet stream winds look like today. All right, let me see if I can switch over here. All right, so let me zoom in a little bit. This website is called earth.nullschool.net. All right, let's let it kind of come into fruition here. All right, now, first, what we're looking at now is the winds down near the ground level, all right at the surface of the ocean or the land. All right, take a look at what's going on here in the Atlantic, all right, in the tropical region from the equator up to about 30 degrees north. We see this strong pattern of winds blowing from northeast to southwest, as I said. All right. Down in the southern hemisphere, you can see a pattern from southeast to the northwest in the Atlantic, and you see the same pattern in the Pacific. All right. Now this pattern is disturbed by weather. All right. For example, right here, right near Hawaii, it looks like there's a winter storm coming through. All right. And so here the air is actually striking a front and going up, though that's difficult to see in this picture. And here you see a large sort of swirly storm pattern. But generally in the tropics, the patterns are pretty consistently blowing from, here we go, from east to west and from the pole towards the equator. All right, this is a hurricane. All right, so the next thing I want to do is to take a look higher up at higher levels in the atmosphere. Now to do that, I need to access the menu over here, which is kind of in the way, my face is in the way of it. So let's see what I can do here. Okay. We're at the surface. I'm going to go up to 500 millibars, about halfway up pressure-wise in the atmosphere. All right, and now you can see something very different. No longer do you have those gentle, sedate winds. Now the winds are really ripping. All right, and up at this altitude, through the effect of the Coriolis Force, deflecting this south to north motion off to its right, we end up with strong winds blowing from west to east. All right, here's the United States, and you can see here's the jet stream flowing across from west to east. Okay, and it, if you look, forms a ring around the pole, that you get a strong west-east wind that blows counterclockwise around the pole. If you go even higher up in the atmosphere, this pattern becomes even more clear. All right, so once again, you can see this counterclockwise rotation of winds, always blowing from west to east. This is the jet stream. All right, these are the westerly winds because they blow from the west. All right, I think this is probably enough for now, so I'm going to call it a day. Please do check out this earth.nullschool.net site if you're interested in taking a look at global atmospheric circulation. Right now, this all comes from weather balloon data. All right. Anyway, I will be back in a couple of days with a video probably from my hotel room in Japan. So, it's been fun, and see you later.